Hi guys. So let's see. I want to talk about the error in the trapezoid rule and in Simpson's rule, right? How we estimate the error in computing integrals numerically using those rules. Okay, first of all, the error in the trapezoid rule. Well, okay, so my diagram shows a function f, right? And oops, didn't really want to do that. And then the trapezoid rule will compute this area. By the way, this is just for a single segment, right? So A and B just cover a single segment of the many pieces that we put together in using the trapezoid rule. So for a single segment, it would compute this area, and then the error would be this area. Now, we already computed that area, right? The other day, or in the other video, we computed the error in the dome on top, right? Or the error in the quadratic part of that area. And we got the formula that area was 4/3 h times alpha, where alpha is this distance, the distance between the linear estimate and the curve at the midpoint, right? The midpoint between A and B. Now we have to make one slight adjustment. The other day, h was the distance from A to the midpoint over here, and then also the distance from the midpoint to B. So in other words, the distance from A to B was 2h, whereas in the current example, doing the trapezoid rule, h is the distance from A to B. So I'm going to write the error is 4/3 h over 2 times alpha, okay, which becomes 2/3 h times alpha. Okay, now I'm going to use the same trick I used the other day. I'm going to assume that we flattened out this bump so that these two endpoints are on the x-axis. So that the function is actually 0 at those points. That won't affect the area. And then we can assume that this bump is given by the function y equals x minus a times x minus b over minus h squared, except that I've replaced h by h over 2. So minus h over 2 quantity squared times alpha. And this is because we know it goes, function goes through the x-axis at a and also at b, right? So that's how we know it's got those two factors in it. Now, what we're going to want to do is rather than expressing the error in terms of alpha, or eventually it'll be more convenient, more useful in general if we express the error in terms of y double prime. So what I'm going to do is I'm just going to point out the relationship between y double prime and alpha so that we can express the error in terms of y double prime. This is a quadratic function. So the leading term, or the highest power term, would be some constant times x squared. And that means that the second derivative would be 2 times whatever that constant is. So whatever the constant is of the x squared term, multiply that by 2, that's the second derivative. So if you work that out, you can easily tell that the constant is actually going to be 4 over h squared times alpha, right? And then multiply that by 2, so we get this formula. The second derivative is going to be minus a alpha over h squared. Right? Then, solving for alpha, we get this, right? And this means that the error is equal to negative. So going back to this is the formula for the error. And I'm just going to plug in now the formula we got for alpha. So we get this. The formula for the error there is negative 2/3 h times h squared times y double prime over 8. Put that all together, simplify it, we get minus h cubed over 12 times y double prime. Now, I don't know if I mentioned this already, but I'm assuming here that the function is actually quadratic, right? So I'm assuming that the curve, this curve here, was actually a quadratic function. In that case, the error is exactly this much. Now, what's interesting to notice, suppose you consider the case when this curve could have been any function, right? Do that again. If this curve could have been, oh, how do you like that? This curve could have been any function. here's an interesting fact. In fact, the error that you get with any function, the error is actually maximized in the case when the function is quadratic. I'll just give you an intuitive explanation for that. The idea is that this error in this area here is going to be greater. You can imagine it being greater if the curve goes up and comes down more, right? If it balloons more. Well, the more it balloons, or in order for it to balloon more, the second derivative would have to be greater. So in fact, you're limited how much this area can balloon out by what the second derivative is of the function. Notice that it starts off, the way I've drawn it, it starts off with the first derivative positive, it ends with the first derivative negative. In order to do this, the first derivative has to decrease, right, from the left side to the right side. And of course, the rate at which the first derivative decreases is the second derivative. So the second derivative is going to put limits on how much this curve is actually able to balloon. And the ballooning will be maximized if the second derivative, it always takes its maximum value. If the second derivative is constant, right? That'll maximize the amount of ballooning that's possible if we always keep the second derivative on its maximum. Right? Well, if the second derivative is always at its maximum, that means the second derivative is constant, and that means that what kind of function has a second derivative which is constant? Only quadratic functions. Right? So it must be a quadratic polynomial. So that describes the worst case scenario when we have a quadratic polynomial. So what we found out is in the worst case, the error is minus h cubed over 12 times y double prime. Right? Now, I'm going to invoke the mean value theorem for integrals. This is the worst case scenario when we have a quadratic function. If we have a less than worst case scenario, we can still use a similar formula. We just replace the second derivative by the second derivative at some point c on the interval between a and b. So even if we're not in the worst case scenario, we can still use a similar formula. We can say the error is exactly equal to minus h cubed over 12 times the second derivative, but now we have to be vague about where the second derivative is evaluated. It's going to be at some point between a and b. But there'll be some point there where this second derivative takes an intermediate value. It's not always at not the maximum value, but it will be the correct value to give us the overall correct value for the error. Okay, so that's applying the mean value theorem for integrals. Okay, so here's the basic formula we want to take away from this, right? The formula in terms of the second derivative at some point c. Now, we want to add up all these errors over the course of an entire integral where we're breaking the interval up into n distinct segments, right, all of with h. So, in applying the trapezoid method to calculate an integral like that, we break the interval from a to b up into n separate intervals, each of with h, which is b minus a over n, right? So yeah, let me just make a note of that. So h would be equal to b minus a over n. And then the error on each one of those segments is what we calculated on the previous page, this formula. So this is the error on each segment, and each segment has its own c value where we calculate the second derivative, and then we add all these up. And now I'm going to invoke the mean value theorem again. I'm going to say that when we add up the second derivative at all of these, well, we add up this term that involves the second derivative at all of these intervals, even though this CI changes for each interval, nevertheless, we can get the total by evaluating the second derivative at some single point C, somewhere between A and B, right? Somewhere between A and B, f prime of C will have the correct average value to make this formula come out right. Okay, so the total error is going to be something like h cubed over 12 times f double prime evaluated at c times n, because that's the number of terms there are here. Right? There's going to be n terms. And then again, using the fact that n, well, h is equal to b minus a over n, that means n is also equal to b minus a over h. If I apply this formula to n here, then we'll see that plugging that in, the error formula becomes this. And this is exact. This is, we're saying the error is exactly equal to minus h squared over 12 times b minus a times f double prime evaluated at some point c. And the trouble with this formula is we don't know where c is, right? But we know c is, all we know is that c is somewhere between a and b. Notice we lost the power of h because n was b minus a over h. Okay, and this confirms what we saw empirically the other day. It seems that the error in the trapezoid method varies like h squared. It's proportional to h squared. And we can see that here. This error term involves the factor h squared. 12 is a constant, b minus a is a constant. F double prime of c is not really a constant, but you know, if we make the optimistic assumption that it's not varying too much, then it's going to be then this will behave approximately like something proportional to h squared. Okay, now with this estimate, we can now get what's called Richardson's error estimate. Now what I'm going to do here is I'm going to use I to represent the true value of the integral, right? So we're integrating some function from a to b. We're using the trapezoid method to estimate or approximate the value of the integral. I is the true value. In is the value that we calculate using n distinct segments, right? Subdividing the integral from a to b up into n segments. And again, h is equal to b minus a over n. Then, according to what we saw on the previous page, we can say that the error is approximately proportional to h squared, right? So, writing it, I can write it this way. Well, h is being b minus a over n, I can say therefore that the error, I minus in, is approximately proportional to 1 over n squared. Right? K is just some constant of proportionality here. We don't know what that is. But we do know, we can say that the error should be approximately some constant k over n squared. If we look at the error in the case where we double the number of subintervals, we replace n by 2n, then the error I minus I sub 2n would be k over 4n squared, because we doubled n, so n squared now becomes 4n squared. Okay? And now we do a little algebra. There's various ways you can do this. I could multiply the second equation, or second approximation, I should say, by 4, and subtract in order to cancel the right sides. And what you get is this. You get this relationship between I sub 2n, and I sub n. And there's two useful ways to rearrange this approximation. We could solve for the error in I sub 2n. I minus I sub 2n is approximately equal to I sub 2n minus in over 3. So you get that just by rearranging the terms in this equation, or approximation. And that's Richardson's error estimate, right? So this is the estimate of what the error is going to be in our approximation using 2n subdivisions, right? 2n segments. That's going to be about 1/3 times the difference between the approximation we just got and the previous approximation. Right? Another useful thing to solve for is just solve for I. I mean, that's ultimately what we want to estimate. So why don't we just take this equation and solve for I in terms of I sub 2n and I sub n. And if you do that, you get this. And I is approximately equal to 4 I sub 2n minus I sub n divided by 3. This is called Richardson's extrapolation because we're extrapolating from the two estimates we just got, I sub n and I sub 2n, and we're extrapolating from those. We're trying to guess what would happen if we continued estimating with bigger and bigger values of n, and we can actually make a good guess for what the ultimate answer would be just based on those two estimates. Notice you can think about this formula. It's a kind of a weighted average of the two approximations, right? We take 4 times the new approximation, I sub 2n. We subtract off the old approximation, I sub n. So the new approximation is counted 4 times. The old approximation is counted -1 time. And we divide by 3 to take the weighted average of the two, right? 4 and -1 means we had a total of 3, a weight of 3 for the whole thing. So we divide by 3 to get the weighted average. And so this is a very, very useful formula. So if you just compute your approximation for 2 values of n, and the easiest way to do that is for values of one value of n that's twice the other, right? So you compute it for n subdivisions and for 2n subdivisions, and then you can use this formula to immediately get an improved estimate for what the final value of the integral should be. Okay, let me show you this. This is kind of interesting. It's kind of cute. It's an alternative formulation of the error formula, right? So we found this formula already, and that one is quite useful. But there's another one that's a different form that's useful in different ways. So let me show you that. I'm going back to actually this. So this was the formula for the total error in the trapezoidal approximation, where we've added up the error on all n segments, right? So as I goes from 1 to n, we add up all the error on all those segments. Now, all I've done here is I took one of the h's. What did I do, actually? Yeah, I took minus h squared over 12 and brought that outside, but I left one of the h's inside, and the second derivative evaluated at ci. This is f double prime evaluated at ci. It's not f to the 4th power, it's f double prime. Sorry about that. Now, what does this thing look like? When you take the sum over a bunch of terms where you multiply h times the value of some function, at some point c, remember c is going to be some point, some x value in the interval, right? On the current interval that we're looking at, right? Each ci is on the ith interval. So what do you get when you do this? Well, this is exactly what a Riemann sum looks like, right? You multiply the width times the height for each one of the intervals. So this sum here is actually going to be an approximation to the integral when we integrate f double prime from a to b. Therefore, we can say that the error in the trapezoidal approximation is approximately equal to minus h squared over 12 times that integral. And furthermore, when you integrate the second derivative, of course, what you get is simply the first derivative evaluated at b minus the first derivative evaluated at a prime. Right? And the advantage of this formula over the other one is that there's no mysterious number c that we don't know the value of, right? This one we can evaluate easily. We can just, assuming we can calculate f prime, and we can just evaluate f prime at b and f prime at a, take the difference, and take h squared over 12, right? Minus h squared over 12. And this gives us an estimate for what the error is on the trapezoidal approximation. And this gives you another way of doing a kind of extrapolation of what the final answer should be. If you've got an error estimate, then you just take this error estimate and add it into whatever value you got for the numerical value of the integral using the trapezoid method, right? We got one estimate for the integral using the trapezoid method. We also got an estimate for what the error is in that approximation. So if we add our estimate for the error to our original estimate for the value of the integral, we get an improved estimate of the value of the integral. So this is called the corrected trapezoidal rule, right? We start doing the plain vanilla trapezoidal method, and then we calculate the error and add it back into our first estimate to get a revised corrected estimate. Okay, so that's kind of nice. Now, let's talk about Simpson's rule. We want to calculate we want to come up with some formula for estimating the error in Simpson's rule. Now, I wrote Simpson's rule. This should be Simpson. Sorry about that. Yeah. The other day I mentioned that in my previous video, I mentioned that Simpson's rule, although it's based on a quadratic interpolation of the function, nevertheless, it actually gives exact results for functions which are polynomials up to degree 3, right? You might naively think that it would only work for, and only be exact for polynomials of degree 2, but actually it works also for polynomials of degree 3. The other day I gave you a rather awkward argument for that. Let me give you a better argument, a slicker argument for the same fact. Let's suppose that f is some cubic polynomial, right? So f is some cubic polynomial, and we're going to want to integrate f from a to b over here. Right? So we want to integrate this cubic polynomial from a to b. Well, what I'm going to do is I'm going to sample f at 3 points, at a, at b, and also at the midpoint, a plus b over 2. Right? So I'll take these 3 sample points, and I'll use those to form a quadratic interpolation of f. So g is going to stand for the quadratic interpolation of f at those 3 points. Then I'll define L to be the difference between f and g. So L is itself a function. It's the difference f of x minus g of x. And the thing is, simply because of the way L is defined, it's the difference of a cubic polynomial f and a quadratic polynomial g. L itself must be a cubic polynomial. So L is a cubic polynomial. Furthermore, the other thing that we know is that L is, let's see, it's 0 at these 3 interpolation points, because f and g take the same values at those 2 interpolation points. That's how we form g, by copying the values of f at those 3 points. So f minus g is going to be 0 at those 3 points. Therefore, L is a cubic polynomial with these 3 zeros, therefore it can be factored to look like this, in this form. It's going to be some constant times x minus a, because a is a 0, times x minus b, because b is also a 0, and it's also going to be times x minus a plus b over 2, because that's also a 0, right? So we just factored out x minus r for each root r, and the roots are these 3 numbers. Now, here's the interesting thing. Because this number, a plus b over 2, is exactly the midpoint between a and b, any cubic polynomial of this form that takes zeros at evenly spaced points like this, it will be anti-symmetric about the midpoint. So this function L is actually going to be anti-symmetric about this midpoint a plus b over 2. In other words, whatever values it takes to the left of a plus b over 2, it'll take the same values but with the opposite sign on the right side of a plus b over 2. That means that when you integrate L from a to b, the integral on the left side will cancel the integral on the right side, and the integral will turn out to be exactly 0. Now that's important because the integral of L is in fact the error in the estimate using Simpson's rule. It's the error in the integral using Simpson's rule. So remember, G was the quadratic polynomial, quadratic interpolation. So according to Simpson's rule, we estimate the integral of f by taking the integral of g. Well, the difference between the integral of f and the integral of g is the integral of f minus g, and that's exactly what L is. It's the integral of f minus g, and we just saw that that's 0. So in fact, we now see that the error in Simpson's rule in integrating a cubic polynomial is in fact 0. So Simpson's rule gives the exact correct value for cubic polynomials as well as quadratic polynomials. Okay, so that's a nice result, nice thing to know. Now what I'm going to do on the next slide is I'm going to replace f by an arbitrary function. So on this page, I was assuming f was a cubic polynomial. On the next page, I'm going to assume that f is an arbitrary function, but otherwise I'm going to carry out the same basic procedure. I'm going to let g be the quadratic interpolation of f at these same 3 points, right? At the 2 endpoints and the midpoint, right, of this interval from a to b. And I'm going to let L be equal to the difference between f and g. And then once again, the integral of L will represent the error in in our estimate of the integral using Simpson's method. Okay, so f now is any function. L is the difference between the original function f and the quadratic interpolation at these 3 points. And therefore, once again, we know that L looks, the graph of L looks something like this. L is going to be 0 at A plus B over 2, and at B. And we know that because f and its quadratic interpolation agree at those 3 points. So L is going to be some function that has zeros at these 3 points. Now, how big could the error be? Well, basically, in order for the error to maximize the error, the error is going to consist of the area in these 2 bumps here. We want those 2 bumps to be as big as possible. So in order for that to happen, then this stuff has to curve as rapidly as possible, right, to increase the error. So using the same informal argument I used last time, I'm going to argue that the error is going to be maximized when this curvature here is constant and maximal, right? So when it's basically always has maximal curvature. Now, in this case, though, what we want to talk about is not the second derivative, but actually the fourth derivative. So if you look at this, I'll tell you, let me try this. If you look at what's going on here, if this is the function, the first derivative, f prime, it's going to look something like this. It's going to be positive at first, then it's going to go down to 0, then it's going to become negative, and then it's going to become, let's see, it's going to become 0 again at this point, and then it's going to start rising, and then it's going to become 0 at this point, and then it's going to become negative. Okay? So that's what the first derivative of this curve would look like. The second derivative then would look something like this. Let's see, would be the derivative. The second derivative, of course, is the derivative of the first derivative. So it's negative over here. It becomes 0, then it becomes positive. Then it becomes 0, and it becomes negative, and then it becomes negative. And then it's going to be, yeah, I think that's what I want, right? So it's become negative, right? So that's the second derivative. The third derivative is going to look like this. It's increasing, it crosses 0, and then it starts, the slope is positive, and then it becomes negative. Oh, I got that backwards. Let me try that again. Right, so the third derivative, let's see, it's positive over here and it's negative over here, so it looks like that. And basically, we want the third derivative to be as extreme as possible, so we'd like its slope to be as great as possible. So what we really want is for the fourth derivative, I ran out of room, but the fourth derivative, what we like this is to be maximal, right? So we'd like the fourth derivative to be as great as possible. So that's how we increase the curvature and ultimately increase the area under this curve by assuming that the fourth derivative is always maximal. Once again, if the fourth derivative of a function is always maximal, then it must be a polynomial. That is, if the fourth derivative is constant, then the function must have been a polynomial. If the fourth derivative is a constant, it must have been a fourth degree polynomial. So again, I'm using the intuitive argument here that the worst case scenario is when L is actually a fourth degree polynomial, right? And in that case, we can compute what the actual area is, area being the error in the Simpson's rule approximation. So from this point on, let's assume that L is in fact a fourth degree polynomial. Then what must it look like? Well, it must look like this. Actually, let me do this. It must look like this because it has a 0 at A, it has a 0 at B, and it has a double root, a double 0 at A plus B over 2, because not only is the function 0 there, but also the first derivative is 0. So it has a double root there. Therefore, the fourth derivative, I'm sorry, the function L, which is a fourth degree polynomial, can be written in this form. Right, some constant k, or negative k times x minus a times x minus a plus b over 2 squared times x minus b. Once again, what we're going to want to do is I'm going to want to express the error in terms of, it's more convenient to express it in terms of the fourth derivative rather than expressing the error in terms of k. So I'll just make a note now of what the relationship is between k and the fourth derivative. The fourth derivative, let's see, in this polynomial, the x to the fourth term is going to have the coefficient simply minus k, right? So the leading term, the highest power term, is going to be minus k times x to the fourth, and therefore the fourth derivative is going to be negative 24k. And solving for k, we get k is equal to negative the fourth derivative divided by 24. Okay, so this will be useful later when we want to express the error in terms of L, the fourth derivative rather than K. Now, using this formula for L, right, remember that's the worst case scenario when L is actually a fourth degree polynomial, we'll just do the integral by brute force here. I'm actually not going to subject you to the whole thing. You can do it on your own time if you don't trust me. But I'm going to integrate this fourth degree polynomial from A to B. Again, I would recommend that you integrate by parts. Integrate this term first and then differentiate first with that term and then this term. You actually have to apply integration by parts twice in order to get this out. So I worked this out. I'm not going to subject you to the whole thing. And what I ultimately got was this. The area under the curve, the integral from A to B is negative 4k h to the fifth over 15, where h, remember, is this, it's actually the difference or the distance from a to a plus b over 2, and also the distance from a plus b over 2 to b. Or in other words, the distance from between a and b is actually 2h, not h, because in Simpson's method, remember, we put two segments together. Each segment has width h, but we do the estimate for both segments simultaneously, right? We join them and perform the estimate for both. Okay, so right, so we get this formula for the error. This is the maximum error that's possible. And then replacing the formula for k in terms of the fourth derivative L, we get this. So this is our formula for the maximum error in using Simpson's method, right? For a single single unit, right, of the of applying Simpson's method, where we apply it to only two successive intervals. Now what we want to do is, as we did for the trapezoid method, to get the overall error on an entire integral using Simpson's method, we have to add up all these error terms for each of the segments. Right? So let's do that on the next page. Oh, by the way, I'm sorry, I forgot one thing. I also want to do the same trick I used before. I want to apply the mean value theorem for integrals to rewrite this formula and to say that, look, this is the worst case scenario, but suppose we're not in the worst case scenario. Suppose f is some other function. It's not actually this fourth degree polynomial. In that case, we can apply the mean value theorem for integrals, and we can say that the error will be equal to a very similar formula. It'll be h to the fifth over 90 times the fourth derivative of whatever f was, but evaluated at some point c, which we can't be sure of. We can't be sure where c will be, but it'll be some point on that interval. I should have written that down too. It'll be some point on this interval between a and b. right? So when we, right, so in the case when we're not dealing with the worst case scenario, we can still appeal to the mean value theorem to say that the average error will be equal to the fourth derivative at some intermediate point. Okay. Now, next, what I want to do is add up, as I said, I want to add up this error for all the segments that you use in carrying out the Simpson's rule for a particular numeric integral. So we want to integrate the function f from a to b. We break the interval from a to b up into let's say 2n segments, and then we look at each pair of segments and apply Simpson's rule to each pair of segments, right? So we're going to have n pairs of segments. The error on each segment looks like this. And then we add them all up. And again, we're going to get two versions of the error formula, just as we did for the trapezoid method. So one version we get by saying, well, if you add up all n of these terms, what you're basically going to get is something that looks like h to the fourth over 180 times b minus a, right? We replace h by b minus a over 2n. Notice this, right? Again, recall that the width of the pair of segments is actually 2h here, right? So remember this picture here. The width of a single unit for doing Simpson's rule is actually 2h. So n equals b minus a over 2h, and so that's where the 180 comes from. And we lost a factor of h here. So h to the fifth became h to the fourth. And again, appealing to the mean value theorem, we can say that when you add up all these, or when you average all of these fourth derivatives at different CIs, it's going to be equivalent to evaluating the fourth derivative at some particular C somewhere on the interval. Okay, so in other words, this error is actually exact. The error is exactly equal to this. The trouble is we don't know what C is. Okay, and then in a similar way, we can get a second formula for the error by interpreting this sum as a Riemann sum and then rewriting it as an integral. So we can say that this error is equal to this sum, which is approximately, or is the Riemann sum of some integral. So it's an approximation to the integral of f to the fourth. The integral of f to the fourth would be f to the third evaluated at b minus f to the third evaluated at a. So we get a very similar formula to the one we got before for the trapezoid rule. And then once again, with this estimate for the error, we can use this error estimate to make an improved estimate for the overall integral, right? So you calculate the integral using Simpson's rule, then you calculate this error, and then you say, well, look, if the error in my calculated integral is this, why don't I just add this to my the approximation I got the first time and get an improved approximation. So you can do that to get the corrected Simpson's rule, right? Start with Simpson's rule, add in the estimated error, and that gives you a better approximation for the integral. Now, for Simpson's rule also, we can do Richardson's error estimate, right? We can do it the same way. So basically, it's the same calculation, just replacing a factor of 4 by a factor of 16, right? So again, if I is the correct value of the integral, the theoretically correct value, and IN is the approximation using n subdivisions, then I minus IN is approximately what's going to be proportional to 1 over n to the fourth. Right? Recalling that n is equal to b minus a over 2h. So basically, n is proportional to 1 over h. Right? So, or in other words, h is proportional to 1 over n. So h to the fourth power becomes 1 over n to the fourth power. And k is just some constant of proportionality. So I minus in is going to be equal to some k over n to the fourth. I minus I sub 2n, well, we replace n by 2n, we have twice as many subdivisions of the interval, and that means this becomes k over 16, n to the fourth, right? 2 to the fourth power 16. And again, you do some algebra here to combine these. What we really want to do is we want to eliminate k from the system. So do some algebra to do that, and what you find is that I minus in equals 16 times I minus I sub 2n. In other words, the error in the previous approximation is 16 times as great as the error in the new approximation. So this is where that factor of 16 came from that we saw the other day in MATLAB, right, when we were using Simpson's method. And then from this, you can then derive two useful formulas, but one is the error estimate. So again, if you just rework the terms in this equation, solve for I minus I sub 2n, that would be the error in the estimate using 2n subdivisions. It turns out that's equal to I sub 2n minus I sub n over 15. And maybe even more useful, we can get Richardson's extrapolation. We can just solve this equation for I, and we get this. We get the estimate that the correct value of I is equal to the value, the approximation we got when we used 2n subdivisions times 16, weighted 16 times, minus the previous estimate when we only used n subdivisions. Again, we're weighting this 16 times, we're weighting this -1 time, so the total weight is like 15. We divide by 15 to get the weighted average of the two estimates. And that's Richardson's extrapolation for Simpson's rule. And okay, so then next what I'm going to do is on the next video, I'll do an example of applying these error estimates in order to figure out how many iterations, how many subdivisions of the interval you want to do to get a sufficiently accurate approximation.